Morning. So yeah, welcome to week 2. Today we're doing analysis of multi-threaded algorithms. Last time we did parallel measures like efficiency and speed up, and this is related to efficiency and speed up, but it's like a more concrete model to express parallel algorithms. Because those are like measurements, but this is like, it's more like a concrete model. So the main model that we're going to be working in today is called the binary forking model, which is a model for multi-threading. And in the binary forking model, basically you have, like in your software, you can create new threads dynamically. And the threads can run asynchronously in parallel, and they do other tasks. And every thread in this model is basically like a standard random access machine. So like the regular theoretical model that you knew in your original algorithms class, RAM, like it's called the RAM model. And in the RAM model, like your machine has a constant number of registers and some memory. Usually in RAM, it's like an unbounded memory, but in this binary forking model, there are multiple processors, and the memory is shared among the processors. And this is like the picture that I showed you in the first lecture. You have multiple processors, and they all get synchronized through this memory. And I'm not going to talk about how you assign this abstract notion of thread onto the processors. That's called scheduling. But for the purposes of algorithms, you can assume that you can make an unbounded number of threads. Obviously, you don't have an unbounded number of processors, but somehow the threads get mapped into the processors. And yeah, so the main way that you express algorithms, yeah, I brought my clicker today, so now I can move. The main way that you express algorithms in binary forking is called fork, or also called spawn sometimes. So basically the way it works is that you start with one thread, and then you can fork another thread like this, or spawn. And now the original thread, which is called the parent thread, and the child thread run in parallel. And they can do separate stuff. They don't have to be related at all. And yeah, and if you need both of them to finish their stuff before you move on, like for example, let's say this was like a function call and you need the results of your function call that you spawned off, then you also have the sync instruction that signals to your algorithm to wait until all the child threads are finished. And the parent thread. So when you get to the sync, then all outstanding threads need to get here and finish their completion, and then only the parent thread continues. And you can continue spawning or forking after that as well. So yeah, you start with one thread and you finish when all the threads end. So like when the original parent thread is finished, then the program is finished. And yeah, this binary forking abstraction, it's simple, but it's actually pretty powerful, and it's supported by several programming abstractions like Silk, which is a programming language, Java fork join framework for parallelism, Habanero, and Intel TBB, which is another popular threading library. It is possible, but when the program is finished, when all the threads finish. But like in theory, when multiple when the parent and children are running, you're not guaranteed which speed they're running at. So it could be like the child thread is running ahead, and that's why you need to introduce sync if you need the results of something. Yeah, does that make sense? Okay. Yeah. So let's do a couple of examples. This is one classical example for parallel programming. So you can kind of naturally see that this fork join parallelism lends itself really easily to divide and conquer, because like you fork off the subproblems basically. So yeah, so let's take this example, this simple recursive program, which is fib. And for fib, there's a base case. If n is less than 2, return n. Otherwise, you have two results, x and y. You spawn fib n minus 1, and then yeah, you spawn fib n minus 1, you continue with fib n minus 2 in your parent thread, and then you sync. And this is supposed to assign x and y to fib, but yeah, that's a typo. Yeah, so you populate x and y with the results of these two, and then you add them up. So fib is like, you add up fib n minus 1 plus n minus 2. Yeah, so this is a recursive algorithm to calculate this. It's not the most efficient algorithm, because as you can see, like a lot of the subproblems are overlapping, but it's just an example for illustrating these parallel constructs. So one thing to notice is you don't spawn both of these because you just spawn, if you have n subproblems, you spawn n minus one of them because one of them is going to be in what is called the continuation, which is the parent thread is going to keep going. Like once the parent thread forks something, then it continues on with whatever is after that. So there's no need to spawn both. Okay, and the thing that comes out of these spawn and sync constructs is called this. It's called a computation DAG, or like directed acyclic graph. And each node in the computation DAG is a, I guess you can think of it as like an instruction or some maybe like a function call, and the arrows denote spawn and sync. And so this is an example. We're doing fib of 4. You start with 4. So this is spawning fib of 3. And then it continues with fib of 2. This is like n minus 1. This is n minus 2. This is n minus 1. And recursively, it goes all the way down until you get to your base case. And then you come back up, and this is the return. This is the sync. So this is return of n minus 1 and n minus 2. Yeah, and this is, so yeah, so the arrows are spawns and syncs, and the nodes in the DAG are instructions, and this is like a dynamic thing that happens when you introduce these parallel constructs. It doesn't have to be defined up front, but it does define the dependencies in the program. Parallel sync waits for all the outstanding child threads to complete, and it says that no threads can continue past this point until all of the threads have reached this point, and then it waits for all the children to complete, and only the parent can go on. Question? Yeah. Yes. So these are spawns here, and then when you sync, like these two threads have to go sync into here. Yes, sorry, that is a mistake because every sync here has 2 arrows going into it. Is that your question too? The light blue nodes are spawns of n minus 2, n minus 2, or like continuation of n minus 2. And then like the boxes are the same, like the same level of doing this part. Like this is n minus 1, n minus 2, and sync. And then this is spawn. Like now we started with 4, so n minus 1 is 3, and it's like n minus 1, n minus 2, sync, and then again like n minus 1 here. Thank you. Yes, I will update it and then upload. Yes. Why do you have arrows going to light blue ones? Those are dependencies, or like there's a spawns and dependencies sometimes. So like you have to finish this spawn before you move on to the continuation, which is n minus 2. Yeah. I guess they are strictly dependencies, and some of them are spawns and syncs, but not necessarily all of them. Because like you need to finish this spawn before you move on. Yes, we just, there should be a line here. Sorry, this is, no, you're good. This is a mistake. I will fix it and upload the slide. Yeah. Good. Okay. Yeah, so like I was saying, the left to right arrows are continue edges, which is the parent thread is doing some continuation. The down arrows are spawns, so those are parallel forks in this model. If you come back up, it's called a return edge. So it's like what you're saying, you need to pass up the result. And these sections, they're called strands, but that's what I was saying, like if that one continuous block. So given these parallel constructs, spawn and sync, you can define this computation DAG. And you can define this DAG, vertices and edges, where the vertices are the instructions and the edges are the dependencies, spawn, sync, and so on. Every vertex is called a strand, which is a sequence of instructions. It doesn't necessarily have to be just one instruction. Like for example, when you spawn, it's probably many instructions too. It's like you have to deal with the scheduler, but it's just like a logical one thing that you're doing. So a strand is a sequence of instructions. And an edge is a spawn, function call, return, or continuation. Those are all dependencies, I think. Yeah. And I didn't talk about parallel for yet, but you can implement parallel for with these spawn and sync constructs, because you can imagine like if you have a loop, you have like n iterations, you spawn half of them, and then like you recursively keep spawning half of them off. So for analysis, you can convert this parallel for to task spawn and then use the recursive divide and conquer. So you have n iterations, and then like the two halves proceed in parallel, and those two halves proceed in parallel, and all the way down. Yes, because in parallel for, if you want all the iterations to proceed in parallel, but you only have fork and sync, what needs to happen? Like you need all your iterations to finish before you proceed from this parallel for, and you want them all to proceed in parallel. So you can, with divide and conquer, fork them all, and then at the end call sync. Okay. So one main question that this computation DAG allows us to answer is, assuming that the strands execute in unit time, what is the parallelism of the computation? And by parallelism, I mean like what is the maximum speed up that you could hope to achieve? This is related kind of to what we were talking about earlier, but this is like more concrete because this allows you to analyze specific algorithms. Okay, so we can go back to Endel's law, which says, it says there's two parts. There's the serializable fraction, like there's a serial fraction and there's the parallelizable fraction. And your speed up is bounded above by the serial fraction. Yeah, for a problem, the upper limit of the speed up is determined by the serial part. Okay, and using Amdahl's law, this is like there's an example computation DAG, and I just kind of like, took the root and shook it a little bit, but so you can see like these are the parallel parts. Like every level of this DAG is, these are dependencies, and the serial fraction is just the longest path through this DAG. Or every serial fraction is like a path through this DAG, and the longest serial fraction is the longest path through this DAG. So the serial fraction is 3/18 because there are 18 nodes, and these parts can all proceed in parallel. So 1, 2, 3 are the parts that need to wait. Okay. We have two notions. Sorry. The serial fraction is 3. So I think serial fraction means like the longest part, like we ignore these parts because they all proceed in parallel. I see. There's an alternative notion. Like I think the speed up is related to the parallelism, and sorry, there is a notion of the longest path through the DAG, but it's called something else that I will go to in a second. And the speed up is related to it, but not exactly that. The speed up is related to the. Let me go forward like 2 slides and then maybe see if that answers your question. Does that work? Okay. Yeah. So there's two notions of performance measures when we measure parallelism. the first one is the work, which is something we were talking about last time. Like we want work-efficient parallel algorithms. And here, assuming that each node is 1 unit, the work is just you sum up all the nodes. So here, there's 18 nodes, and the work is 18. And yeah, and so like the main notion that we introduce when it comes to parallelism is called span, which is the longest path through the stag. And parallelism is related to the work in the span. And speedup is also related to the work in the span. So the span is the longest path through the stag. You can think of it as, like you were saying, like you have to, if you had infinitely many processors, you couldn't do faster than this because you would have to go through this chain of dependencies. Yeah, and the span, of course, is bounded above by the work. You can also call it depth. In some of the papers, it's called depth. So yeah, but the speedup is not 9, or like it's not 2 either. Wait, sorry. The speedup is not 9, and it's also not 3, or like 6. It's related to the work in the span. You can't get more than, I guess like there's no clear relationship between just the span and the speedup. Yeah. So the work law, yeah, this is kind of what we were saying last time. Your parallel time is bounded, you can only get p speedup at most, and the span law, your parallel time cannot be any faster than your span. Yes. I don't know where it is on the slide. It's probably further down, but if you divide the work in the span, that's called parallelism, and parallelism is like an upper bound on how much speedup you can get. The t sub p is the parallel time, and your parallel time cannot be faster than your longest chain, because the longest chain is the time on infinitely many processors.
Yeah,
it can't be shorter. Like parallel time is at least infinite time.
Okay. Oh yeah, no, never mind.
Hmm?
Parallelism and like almost the same.
Parallelism is an upper bound on the speedup. Yeah, parallelism is like if you had infinitely many processors, how much speedup could you hope to achieve? Does that answer your question? Thank you. Yeah. Okay. So there's a couple of expressions that we can give about the work in the span. The work, say we have these two functions, I guess, a and b, and they're proceeding in series like this. The work of them together is just the work of both of them summed up, and the span of them together is the span of them summed up because they have to proceed in serial. If they were parallel, the work is still both of them, just added up, but now the span, you take the max of both because they're separate. Yeah, so this is the definition of speedup that we had last time. The serial time divided by the parallel time is the speedup on p. T sub p is the time on p processors, T sub 1 is the time on one processor, and speedup is serial time divided by parallel time. If it's less than p, that's called sublinear speedup. If it's equal to p, then we have perfect speedup. And if it's greater than p, that's superlinear, which is not possible in this model, but possible in reality sometimes. Because like if you have p processors, you imagine each of them can do one step at a time. So the most that you can do is like p steps at a time. The span is unrelated to the number of processors. Like I said, the span is your time if you had infinitely many processors. And yeah, usually for simplicity, like from a theoretical standpoint, we assume that there's infinitely many processors. Of course, in reality, we have a bounded number of processors. But we learned from Brent's law last time that you can simulate more. If you get an algorithm that runs on more processors, you can always run it on fewer processors. So that's like an alternative. This is an alternative formulation of Brent's lemma that we had last time, which is like your parallel time is at least your serial time divided by p, and it's bounded above by the span plus serial time over p. This is like if you simulated your infinitely many processors on p processors. Okay, yeah. So this is like what I just said now, which is parallelism. And these, yeah, so the parallelism is the serial time divided by the work divided by the span. And in some sense, it's like the average amount of work per step along the span. So like, because you get the span and you get the number of work units and you divide them. And so here in this example, it's 2. And yeah, this bounds the maximum speed up that you could possibly get. Okay, so going back to this example that we had in the beginning of fib, the work is 17, the span is 8, and the parallelism is about 2, a little bit more than 2. And so for this particular call of fib of 4, like even if you had more than 2 processors, it wouldn't really help you. Is that good so far? Yeah, because the parallelism is an upper bound on the speed. The parallelism is an upper bound on the speed up. Because you can think of the parallelism as like work units per span, kind of. Per unit of span. So you're bounded above by the span. Sorry. The fastest, you're bounded below by the span. The fastest you could possibly do is the span, because that's the time on infinitely many processors. And parallelism in some sense is like how many parallel steps are there that you could do per step of the span. So that's like here it's 2-ish. So that means like if you had more than 2 processors, they wouldn't have anything to do, because at most, on average, there's like 2-ish parallel steps that you can do per depth step or span step. Does that make sense? So you can do another. The rest of this is mostly examples, but I think that they're useful. Let's go to quicksort, which is a classic sorting algorithm. Quicksort takes this left and right. If left is equal to right, then you can finish. You have to do this partitioning step for left and right. And then you can do the 2 halves in parallel. But let's ignore for now parallelizing the partition step, assume that it runs in theta and work in span if you just do it serially. And then you sync at the end. Does this make sense? How you would parallelize this? Ignoring the hard part of doing the parallel partition. Okay. So for this one, what is the expected work in the span? You can start with the work. So this step is n, this step, and then these are 2 recursive halves. Does this change the expected work of quicksort? You say no, why? Oh, sorry, in the black shirt? I saw him like shaking his head. Yeah.
I was just thinking that all the calculations will still happen, which
Mhm.
are part of the work.
Mhm.
The work should still.
Yes, exactly. You can get the work if you just remove all the parallel constructs. So, because that's the serial time, like if you just ran it on one thread, that would be the work. And this is just the same as normal quicksort. Like there's a linear partition step, and then there's normally in quicksort you just call these 2 halves. Now these 2 halves are in parallel, but it doesn't matter because you're not adding more computation. So exactly. Okay, so yeah. Oh, I shouldn't tell you the span. Yeah, we can go back. What is the span in the binary forking model? I'll give you a hint. It's determined by the partition step. The span is the longest path. So like the
Partition and two steps in it. Because the two quicksort steps will be running directly.
yes, exactly.
So for span will be considered one quicksort and the partition.
Yes. So what would that be?
Log of n raised to.
Log of n. So you have to, okay, so what is the span of this partition step? And assuming that you do it serially. Yeah, so the span is at least n, right? Because you have to do this serial partition step first, and in the beginning, left and right are n. And then what about, and then you spawn the quicksorts, and assuming that they get cut in half. So then, as you say, like these are now in parallel, so the next step down would be like, say if this was size n over 2, this would be size n over 2, and so on like that, right? So does it make sense that the span is at least n? Because you have to do the serial partition step, and then you just go all the way down in your recursion. But now the spans are like, now like the two halves are partitioned in parallel. So the work is still n log n as it was before, and the span is, the expected span is n, because you have to do this initial serial partitioning step. So for parallelism, that gives you log n, because you just divide the work in the span. Span is at most n. The span is theta n, I guess, because you're doing like n plus n over 2 plus n over 4, so on, so on like that, and that series is 2n, or it's bounded by 2n. Does that make sense? Yeah, so good question. So the first level of the recursion, this was n, this partition, assuming that we cut it approximately in half. The next step down, the partition is n over 2, one level below that, n over 4, n over 8, like that, all the way down. And if you add those up, that's bounded above by 2n, which is theta n. Thank you. Okay. You don't have to actually look at this in depth. This is just the work and the span of several practical algorithms like merge sort, matrix multiply, Strawson's matrix multiply, and a bunch of others. I'm going to go through some of these in detail. Like we'll do matrix multiply and Tableau, I think, today. You don't have to remember this table. It's not going to be on the test. Okay, so that is that section. Are we good so far? Okay, so the next section is going to be about divide and conquer, because like I said, this fork join parallelism lends itself very easily to divide and conquer algorithms. So the one common method to solve divide and conquer recurrences is called the master method, or master theorem sometimes. And it basically, you take, it gives, like given recurrences of this form, T of n equals a times T of n over b plus f of n. It gives you a closed form formula for, or gives you a closed form solution of recurrences of this form as a function of like a, b, and f of n. This should say, this is a typo, it should be a at least 1, b greater than 1, and f is asymptotically positive. And there's a base case, T of n is theta 1 once you get sufficiently small n. Okay. And the way this works, like, is you start from the recursion tree. So we start with T of n at the very top of this recursion, and we're going to have a subproblems of size n over b, because like as given by the recurrence, a t n over b, a is like the ways that you're going to divide this, the number of copies of this problem that you're going to have, and n over b is the amount by which the problem shrinks. So and then plus f of n, because that's just like the extra term that we had to do at every level of the recursion. So we get f of n on the top. Like I said, you have a subprop, you have a branching factor, and over b is each one of the subproblem sizes. And then again, you keep going down. So like each of these now is f of n over b, and then you get b over b squared all the way down until you get to t of 1. Make sense? Okay. So this is your recursion tree, and there's several cases. Oh, okay, yeah. So the height is log base b of n, because every time you divide it by b, and this is how much work there was at every level. So f of n, you had a subproblems times f of n over b, again, you had a squared, f of n b squared, all the way down. This is the most important part, I think, is the number of leaves that you're going to get. And the number of leaves is the branching factor raised to the height times t of 1. But we said that t of 1 is going to be theta 1. So this is just the number of leaves. Yeah. So Lester's theorem kind of based on this recursion tree. And it tries to make some argument about basically make some argument about the branching factor. And the way you can think of it intuitively is like how many leaves are there relative to how much you started with at the top. Because if there are a lot more leaves, then the work is dominated by the leaves. So there's 3 cases in the master theorem. One is that all the way down, like I said, the levels are geometrically increasing. So that means n to the log base b of a is much greater than f of n. Yeah. Yes, n to the log base b of a is much greater than f of n, which means that the branching factor is much greater than the work that the little bit of work that you're doing at each node. And so that means the work is dominated by the leaves. This n to the log base b of a is just the number of leaves that we had. The other case is if it's arithmetically increasing, so it's not increasing so dramatically, the number of leaves n to the log base b of a is similar to f of n, which is the work at each level. And that means this is just like you get a log factor in the work because you have log levels. Yeah. So if f of n is similar to the number of leaves times some polylog factor in n, then the solution to the recurrence is the number of leaves times one more of that log. Because you had log levels and like you had log work at each of them ish. And the last one is if it's geometrically decreasing. Oh, sorry. Yes. So we got the f of n function, which is the work that you have to do at each node. And if the f of n work that you have to do takes this form, which is order of, and this is the number of leaves that you have, and this is some log factor in the work. Like this came with f of n already. You don't have to figure that out. Then this is just saying the closed form is one more power of that because you have log n levels. And you have log n levels in the tree, and each one of them has to do this like log n-ish work. Good, thank you. Okay. And the last case is if it's getting smaller. So that is the number of leaves is much less than f of n, which is your function. So that's saying like the work is dominated by the top of the tree. If f of n is very big, and so solution to that is just your recurrence is theta f of n. And then there's some other regularity condition that you have to satisfy. Yeah, so those are the 3 cases in the master theorem, and that just allows you to jump straight to the solution of the occurrence. There are more complicated theorems like Acrobazi that allow you to solve different kinds of recurrences. No, we're just doing master theorem. Okay. Yeah, so this is just summarizing what I said before. I'm not going to go over it again, but those are the three cases in the master theorem. Okay, so let's just do a couple of examples. This is just a few recurrences. The first one, t of n, is 4 times t of n over 2 plus n. So here, f of n is n, a is 4, and b is 2. So n to the log base b of a, which is the number of leaves that you have, is n squared. And that is greater than, much greater than n, which is f. Like, you're comparing basically n raised to the height. You're comparing the number of leaves to f of n, which is like the work at each level. And so the first one is case 1, which is you have many more leaves than like the number of leaves is much greater than the number at the top. So the work is dominated by the leaves, so that is theta n squared. However, if you make f of n squared, now this is case 2, which is arithmetically increasing. And this thing, so this is like the number of leaves you have times, this is like the log k thing that we were saying earlier. K can be 0. So this is n squared, so the log raised to the 0 is just 1. K is from this case. So case 2, if f of n is of this form, number of leaves times log raised to the k of n. Or this is just like the form that the master theorem covers, which is if your function is equal to the number of leaves times log raised to something, then the result is just number of leaves times one more log than that. Yes. Mm-hmm. Thank you. Good. Yes. So, and k can be 0. So like, so this is saying like maybe you may have number of leaves. Like if your f of n is equal to the number of leaves, then you would get log k plus 1, which is an extra log factor because you have log levels and each one is doing f of n work. Okay. So yeah, your number of leaves is n squared. Your log k is equal to 0 in this case. So then by the solution of the theorem, you get n squared times log n. K plus 1 is 1. And this last case, t of n, if we made f of n n cubed, now n cubed is much greater than the number of leaves that we have, so the work is dominated by the top, and that is n cubed. Then there's some cases, like we were saying, that the master theorem does not cover. This f of n is not covered by any of the cases, but we will not have to do that in this class. Okay. Yes. Oh, sorry. Did you have a question? Oh, sorry. Yes. Okay. All right. So that is the end of this theorem on the master section on the master theorem, and we can move on to parallel loops. Okay. So, like I said, you can implement parallel loops with divide and conquer. And if you have a parallel for loop with n iterations, it has span log n in the binary forking model because you just spawn half of them. You spawn half of them at each level, and that the height of that tree is log n. Yeah. There's an older model called the PRAM model, which is direct extension of the RAM model, and basically that assumes that you have infinitely many processors that can all, yeah. And in my view, the main difference between this and that is that here a parallel loop, parallel for with n iterations is span log n, but in here it'd be span 1. So the spans are most like polylog factors away from each other, but we're going to be working in binary forking, which has the span log n. Yeah, and this is just how you would write parallel for. Okay, so let's do a small example. This is matrix transpose. You just you're swapping along like the diagonals. And this is the serial version of matrix transpose. You have 2 loops for I up to n, for j up to I, you just swap I of j and j of I, or sorry, aij and aji. You just flip them. Okay. What is the work in the span? In this, so one way to parallelize this is we can put a parallel for on the top loop, because all the rows can proceed in parallel. What is the working span of this algorithm in the binary forking model? So we could start with the work. What is the, like ignore the parallel for 1 second. What is the complexity of the algorithm, like the work complexity? Yes, good. And the span? And log n. Why is it in log n? I'm not saying you're wrong. I just, it's just a follow-up question.
So previously there were one loop inside another, each taking n times, so it will be n square. Now we are breaking that the first n into log n, because like for parallel for it will be log of n, the span is log n. So the first one is broken down into n, but still like the inside loop is like serial, so it will be again n, so it's n.
Yes, good. Exactly. So does that make sense to everyone? The outer loop has span log n, and the inner loop has span n. So, and then the inside is just constant swap. So the span, you compose them log n plus, wait. Wouldn't it be log n plus n? Because the span is log n, like you're composing them. It's definitely at least n, because the inner loop is n. But you may not need to multiply by log. N? Yeah, I think it's n because you don't multiply the outer loop by the inner loop, you add them. Or you take the max, actually. But in asymptotics, adding is the same as max. Yeah, exactly. So the span is n, which is the inner loop, plus log n, that is n. And the work, as you said, is n squared, so parallelism, you just divide them. Mm-hmm.
So in that case, it's been also
Yes.
does that mean like you're just doing two at a time, all at once?
In this example, it didn't. Yeah. But for example, like in the, if you just had a parallel for, like in PRAM, that would be 1. But then in binary forking, that's log n, because you have to do this divide and conquer.
It's like the longest path.
Yeah. So the reason that it wasn't changed here is because the main factor is this n, which is the serial part. You have log n levels of the n operation. Yeah. Let me put this up. Actually, maybe not, because there are not markers. Hold on. No. Thank you. So this is like n. Like this, you mean? These are like your loop iterations. So this is the outer loop. Yeah, so the height of this is of course log n. And then once, so the actual iterations are down here, like 1, 1, 1, whatever. And in this for loop, like they go up to I. So if this is like, for example, I equals 1, I equals 2, so on, this would be like the span of each of these iterations is like 1, 2, 3, up to n. Does that make sense? So like the span would be the height of this tree. Once you get down, then you're actually doing the iterations, and that's plus n.
I know it goes away, but where does it come from?
It comes from the height of this tree. you have to, in binary forking, you start with n iterations and you fork all the way down. Like you have to keep forking until you get to the bottom and then you do the loop.
Right. So, but it's the parallel fork that sleeves is binary forking.
Mhm.
Oh, we're just saying the parallel fork is binary.
Yeah, we're saying in the binary forking model, the way that you implement parallel for is through divide and conquer.
Okay. Right. So the parallel fork can also just be all n run parallel.
In PRAM. Yeah. So in this particular problem, it wouldn't matter because you still have to do the n serial part. So the span would be dominated by n. But if it was a simpler loop, then you would see some log difference. Yeah. Even if you could do this parallel for in one, like if you could spawn infinitely many, you would still have to, like the longest inner serial part is n. It would be n plus log n because the height of this tree is log n, and then so the minimum, the span of just creating the parallel for is log n.
Okay, so we are assuming that each step is not.
Sorry, we're assuming that to fork takes unit time.
Okay, so it's taking time, and then so log n, and then we add.
Well, this is just the number of iterations. Like you don't have to add them. This is like you have n iterations to begin with, and this is saying you're running these two halves in parallel. So now there's n over 2 iterations and n over 2 iterations running in parallel, and you keep doing that down. So then these 4 are running in parallel. And then you keep doing that until you get to one single iteration, a constant number of iterations, all running in parallel. Like each subproblem. Now the leaves are, you can think of them as 1. So the height of this tree is log. So the height of this tree is log, so you have to incur log n span to just kind of, in some sense, like create your parallel for. And then once you create your parallel for, that's the outer loop. And now the inner loop has however long it will take. And then that is dependent on I, which goes up to n. So like the longest inner loop is n. So that's why it's plus n. Good question. Yes.
Parallel the multi level. There will be in place transpose.
Yes.
There will be.
Would there be?
In place. So, like, if each node transpose each row, there will definitely be there transpose a row to a column. Column is another row's part of another row.
But this is just doing the lower triangle. Like this loop goes over the lower triangle. So you swap with the upper triangle. Good. Yes, good question. So let me repeat that because that was a good question actually. So why is this okay? Because if this loop nest went n squared, then like you're not guaranteed that the threads run at exactly the same time in lockstep. So like what if something, you're trying to swap kind of like in some sense the lower triangle with the upper triangle in transpose, and you want to make sure that like the thing that you're swapping is not changing from underneath you from another thread. And the reason that we guarantee that that is fine is because this inner loop goes up to I, and then the outer loop goes up to n. So that is like that's like the lower left triangle doing the transpose. Yeah, so you can, because it's safe, you can actually put a second parallel for there. Yeah, so what is the work and span in that one? Yes, good. And how about the span? Good. Log n? No, just log. Because you have 2 of these, so you just, no, you're good. So this would be 2 log n, which is theta n, or theta log n, sorry. Yeah, so the work is still n squared. The span is log n because each of these parallel fours has log n, but they're like one after another. So you add them up. That's still theta log n. The parallelism is you divide them. Yeah. Yeah. Let's just do it. Exactly. So like now, this is now instead of like this, like we get to 1 here and there, and then now we make another like n over 2 all the way down. Okay. Yeah. So yes, this is just like a cautionary now. So there's two ways to write this parallel 4. One is you put the parallel 4 on the outside up to n, and then you go up by 32 each time. And each on the inside, you just do a serial loop over the 32-ish, or whatever remainder is at the very end. And this is just adding up like two vectors, a plus b. The work of this one is n, the span is log n, and the parallelism is n log n, n over log n. However, another way to do it is, or one thing that you shouldn't do is make this go up by p. Like if you knew you have p processors, one maybe natural thing or one thing that you might think to do is you just assign each of them n over p iterations. And then you do serial 4 over the n over p iterations. However, the span is then n over p. So the parallelism is theta p, which is not as good as n over log n.
When we look at these parallel forwards, I'm always kind of assuming that there's infinite processors.
Yes.
But are there like actual parallel for functions and languages mentioned at the start?
Mhm.
Okay.
Yes, yeah. Often they're just syntactic sugar over divide and conquer.
They usually have like a way of like, not using 10 processors or
Not using, like if you want to use fewer processors?
like third processors, like in reality.
Yeah, like in reality, in some of the libraries, you can set the the maximum number of processors that you want to use. And there's also a Linux command to limit the number of cores that you use. Like outside of that's one level up from the actual language. That's like a command line thing that you preface your binary with. Does that answer your question? Yeah, this is just saying not to divide. So if you know you have p processors, this is just saying not to divide up your loop by n over p. Like one thing that you might think to do is you're like, okay, I have n iterations and p processors. Let me just put a parallel 4 over them and give each of them n over p iterations. However, like if we analyze them, the span would then become n over p because the inner loop, which is serial, is over n over p. And then the parallelism is now theta p, whereas if we just instead like cut it up by constant chunks, like here 32 is a large enough constant, then the parallelism would be a function of n rather than a function of p. And the example for this 32 is just often in these languages you don't have to implement them, but like usually when you do the implementation, you don't want to recurse all the way down because there's some overhead to forking. And so like forking just one small iteration is often not worth it. You want to fork like enough stuff. But sometimes languages will just do this under the hood for you. Oh yeah. You want parallelism to be much greater than p because parallelism is the upper bound on speed up. Okay. I don't know if I want to talk about this, but maybe. Okay, so yeah. So to get maximum speed up, you want to minimize the span because parallelism, which is the max speed up you could possibly achieve, is t1 over t infinity. And if you make the bottom thing smaller, then the whole thing will become bigger. In practice, try to make at least 10x parallelism compared to the number of processors that you have. If you have a lot of parallelism, sometimes you can trade, like what I just showed earlier. Instead of making your outer loop instead of just doing your iterations one at a time, you can make them like in bundles, and that trades some of your parallelism to reduce the overhead of doing the forks. You can use divide and conquer. Yeah, you should use divide and conquer parallel loops rather than spawning one thing at a time. So you should use this parallel for, not serial for and then spawn, because the span of this is like bounded by the above. Yes.
That bottom is like the logical classical code.
This is each iteration is running in parallel. This is for an outer serial loop, each of them is forking something. So this is going to take span n. This is going to take span log n, because like, does it make sense? Like this thing has span log n on the outside. And then this thing, I guess, has work 1 or span 1, theta 1. However, like using this parallel for construct does this divide and conquer thing. Yeah. So you want to make sure that you don't spawn too much. This is not really important from a theoretical perspective, but from a practical perspective, if you're doing forks, like you want to only fork off the work when there's enough of it to make it worth it for another thread to do, because often the fork overhead may be greater than like an individual loop iteration's work. Usually it's, if you have to choose between parallelizing outer loop and inner loop, it's better to parallelize the outer loop, because then there's like more work per processor that you're forking off in some sense. And last one is watch out for scheduling overhead. This is related to the previous one of like, when you fork work, there is overhead, like the scheduler has to deal with it to assign it to some processor. So yeah. Yeah, and the reason that you want to parallelize outer loops rather than inner loops is because here, like in this example, if the outer loop runs over n and is serial, then like your span is already n. Good.
On the previous slide, why is the span n?
So just ignore what's in here for a second. Like the span of this outer loop is n, because it's a serial for I0 up to n.
So isn't the span just like when you spawn new threads, it creates a new node, and so that
Yeah.
flow is in one thread.
So like, can visualize like this would be like n. 1, 2, up to n, and each one of these is doing like a spawn.
But isn't it just like the? Oh, I see.
You good? Yep, thank you. Okay, let's move on. Okay, yeah, so we can do an example. We're going to do matrix multiply. So for simplicity, let's just do square matrix multiply. You have your matrix output C, you have A and B, and basically for every entry of C, you're doing like some, in some sense, like you're doing like a dot product of A and B, like this. Yeah, and for simplicity, because we're going to do divide and conquer, we're going to assume that n is the power of 2. Yeah, so this is the easiest way to write matrix multiply. You have 3 loops, I, j, k, all up to n, and you can parallelize this. You just put parallel 4 over I and j. So again, like the output is Cij is equal to some summation, and then you have this moving dimension, which is k, which is the inner one, and that's just in the dot product. So the work of this is n cubed. I think we did this last time. There's n cubed iterations. The span is theta n, because we have 2 outer loops, which is log n plus log n, and the inner one is n. So the span is bounded by theta n, and parallelism, you divide them. N cubed over n is n. Yeah, and as an example, for 1000 by 1000 matrices, the parallelism is n squared, which is like 10 to the 6. So that's probably more than the number of processors you have. Yeah, so that is the iterative version. And another way to formulate matrix multiply is through divide and conquer. So rather than doing like these 3 loops, we can cut the matrices into quadrants. 0, 0, 0, 1, 1, 0, 1, 1. And you just cut all of them into quadrants, and you can express them recursively as submatrix multiplies. And there are 8 submatrix multiplies. Yeah. And then you have to do these 8 multiplies, and then you just do this one add of 2 matrices. Does this make sense? Have people seen recursive matrix multiply before? This is just like if you can think like if all of these elements were just one single entry, this would be like A0, A1. Like this is just like the row and the column product. Just add them up. Okay. Yeah, this is about. I don't know if this matters too much. This is about just like their matrix representation. So if you have a matrix, the way that one common way to lay it out of the memory is that you put all the rows like one after another. So you put like row 0 and then row 1 and so on. And that's called row major because you can think of your memory as like a flat layout. And then this is just telling you how to index into your matrix. Like if your dimension is n sub m, then to get row I and column j, you do row length times number of rows plus column. And it doesn't really matter how you store your matrix, but I think this is just because when we write code, like you have to pick some storage method, so you have to index into it. Okay, so this is how you would index into it for divide and conquer. This is how you choose like the corners. We're trying to cut this into n by 2 submatrices. So in each step of the divide and conquer, the matrix length is going to get cut in half, and the matrix size is going to get cut by 4. And this is how you write this divide and conquer matrix multiply. So restrict just means that it's telling the compiler that the matrices are not the same location in memory. And yeah, those are just the parameters, n sub c, n sub a, n sub b, which are the dimensions of your matrix. We're assuming that they're square. Yeah, they're just n by n. And there's a base case, which is below some threshold. You do the serial base case, like the 3 loops. And otherwise, here in this case, we had 2 matrices that we were trying to add. Like if you remember the recursion, so we need to allocate this spare matrix to store like the second matrix that we're trying to add together. And then that is equal to the size of the initial matrices. And yeah, this is just computing the indices. This is the main parallel part. So you can do all of the 8 submultiplications in parallel. If you remember, like we're trying to add 2 matrices, and 2 matrices are created by 8 submatrix multiplies. There's 4 in each one. And yeah, so there's 8 subproblems. They can all proceed in parallel. And then we have to wait for all of these subproblems to finish before we add them. Yes, good question. This should be like probably this last one would be in the continuation. Yeah. Good call. Yes. Yeah. So they can all proceed in parallel. You wait for the last one. You wait for them all to finish before you proceed, and then you just add them up. That's it. And then add is just like you can do the add in parallel. Like every just matrix addition, you can do every entry in parallel. Yeah, and that's it. Okay. So let's start small. We have to analyze all the parts anyway. So for matrix add, there's 2 parallel 4s, and the inner one is just you add the matrices the same index, and the work is n squared because the matrices are size n squared, and the span is log n because it's just 2 parallel loops concatenated over each other. Okay, so using the master theorem, we can analyze this recurrence. There are 8 subproblems. Each of them has size n over 2, plus theta 1. Or, yeah, plus the cost of addition plus theta 1. So, yeah, this is A is 8, B is 2, and f of n is n squared. And the number of leaves is n cubed, right? Because log base b of a, log base 2 of 8 is 3, so n cubed. And n cubed is much bigger than n squared, so the work is dominated by the leaves. Okay. To analyze the span, we just have all the problems can proceed in parallel. So there's just one, there's no like constant in front. A is 1, because you just take the max, and the subproblem is size n over 2. The span of sum, we just did that with log n, so this is log squared by master theorem. F of n is log n, log base b of a, like that. And then so k in this case was 1, and then k becomes 2 in case 2 of the master theorem. Okay. Yeah, so the work is n cubed, the span is log squared n, and the parallelism is n cubed over log squared n. And that is pretty huge. Yeah, are there questions on that part? Does that make sense? Okay. Yeah, so for now, like this initial algorithm, you need to use temporary space. So one possible source of inefficiency is that we had to allocate another n squared matrix, which is not ideal. And another thing is, yeah, so we want to minimize the extra stores that we can use. So one trick often that you can play in parallel algorithms is if you have a lot of parallelism, you can trade off some of your parallelism for space savings. Like instead of doing all these subproblems in parallel, we're going to do some of them in parallel to avoid using the extra temporary. And so that's kind of, yeah. So that's gonna be how it works. And again, these should be like, the last one should be in the continuation, but okay. So this is another version of this divide and conquer matrix multiply that instead of doing all the 8 subproblems in parallel, this does 4 at a time and then 4 at a time. And the reason that you can do that, or the reason that you might be interested in doing that is because now you don't need to allocate the temporary, you just have your output matrix C. Yeah, and now you notice like there's no add anymore at the end. Yeah, you can reuse C, and the work is the same as before. Even though the recurrence is different, this used to be n squared, and now this is 1. But it was in case 3 of the master theorem, so the leaves are still the main factor, and the work is n cubed. And the span is now 2 times this thing, because previously we did all 8 in parallel, but now we're doing 4 and 4, so it's like 2. And plus 1, so the span is theta n. Using the master theorem, the number of leaves is n, f of n is 1, so the number of leaves is the dominating factor. Okay, so we traded a little bit of parallelism, so now the span is n rather than before I think it was like log squared, but now the parallelism is n squared, which is still pretty large. And in practice, this version is faster because you don't need to do the allocation, which we didn't talk about in the asymptotics, but actually allocation is slow.
So it's adding like the first 4 sets to like the first 4 sets. So that's why the unique it's just accumulating overall.
Exactly, yeah, exactly. And we couldn't, but we had to synchronize before because otherwise we may overwrite. If we did all 8 in parallel, you need the temporary, otherwise you may overwrite some of the results. Good. Questions? Okay. Good. So I only have like 5 minutes, but I can finish next time. So we'll do merge sort for a little bit. Merge sort is a recursive sorting algorithm. The main interesting part for parallelism is the merge, because like this is kind of like quicksort in the same way. Like the partition was the main factor in quicksort. In merge sort, the merge is the main factor because the rest is just divide and conquer recurrence. And merge, this is just some pseudocode for it. Oops. You get C, you have A and B, and you want to merge A and B into C. And this is just doing like two finger stepping. Like you have a pointer in A, you have a pointer in B, and assuming that they're all sorted, then you can you just advance whichever one is less, and you copy that into C. Make sense? Okay. So, like I said, merge sort, you spawn the two halves, you sync, and then you merge. This is after this, both halves should be sorted. Yeah. So the work is unaffected by this, similar to in quicksort. Work is still n log n. 2n over 2 plus theta n. Actually, I think this is, you can, this is like by the master theorem, because A and B are the same. So f of n is equal to the thing, and k is 0, but then k becomes 1. I don't know what I meant to say. Doesn't matter. Oh, cool. Okay. Yeah, the span is, you have n over 2, because each of the halves can proceed in parallel, plus theta n, which is the span of the initial merge, which is theta n. Okay, so the work is n over log n, the span is theta n, and parallelism is log n, which is very small. You want, ideally, parallelism much greater than log n. And the way we're going to do that is by parallelizing the merge. So the way that you parallelize merge is you have these two arrays, assuming that they're sorted. And basically the way it works is you pick the midpoint in the bigger one, you search for it in the smaller one, and now you can recurse on the two halves because the two halves are like in the same range. Make sense? So yeah. So one trouble about this is, or not trouble exactly, but one difficulty about this is you cut at each level of this recursion, you cut the bigger one in half, but you're not guaranteed to cut the smaller one in half. In fact, it's probably not. Like it may be totally imbalanced. You may have like n over 1, n minus 1, and then 1 on the two sides. Yeah. And basically, the way this proof works is because we cut in the bigger one, we're going to prove that even if you get this worst case splitting, that the total number of elements in the bigger half is up to 3/4 n. So you still get some constant split. Like it may not be exactly half, but as long as it's a constant, the height of the tree is still log. Okay. So this is just the code for this parallel merge. You split the bigger one, n over 2. You do this binary search into the smaller one, which is b. You, I guess you copy this in. This is the initial one, and then you spawn the two halves. And then this top one is just like you make a the bigger one. So if you get to some level and they're not in the right direction, then you just flip them. Okay. So the span is t is bounded above by this 3/4 n over 4, and then the span, the additional f of n factor is log n, because the binary search has span log n. And this is log squared by the master theorem. Wait, hold on. Yeah. So yeah, these are the subproblems. Oh, sorry. This means to say work, I think, because T sub 1 is work. But p sub 1 of n is complicated because you get these split into non-equal halves. Like with span, it was easier because you can just take the max. And if you cut it by a constant factor, like the max is still fine. But here, the work, you have to take the sum for the work because you just can't take the max. So if we split it, this is just like however we split it, like alpha and 1 minus alpha, which is a constant split, but still not necessarily equal to 1/2. And then we can prove that alpha is bounded between 1/4 and 3/4. And then I claim that this is still theta n. This is not covered in the master theorem, but you don't have to prove something that complicated. I'm not going to do this now. Also, I'm out of time, so we're going to continue next time.